The morning of March 8th, 1945, Lieutenant Colonel Harvey Fraser stood at the western approach to the Ludendorff Bridge at Remagen, Germany, staring at a problem that defied every engineering principle he'd been taught at West Point. The bridge was damaged. German demolition charges had weakened its central span. The deck was cratered. The superstructure showed visible stress fractures. His orders were clear: move 400 Sherman tanks and their supporting vehicles across the Rhine River in 36 hours. 400 Shermans, each weighing 33 tons, each representing millions of dollars in manufacturing capacity and months of production time, each carrying a crew of 5 men whose lives depended on the bridge not collapsing beneath them. The Rhine was the last natural barrier protecting Germany's industrial heartland. Every hour of delay gave German forces time to regroup, to establish defensive positions, to bring up reinforcements. General Eisenhower had been explicit. The bridge at Remagen was the opportunity of the war. Use it or lose it. Fraser walked onto the bridge deck and felt it shift beneath his boots. The steel groaned. Rivets popped. The entire structure was moving in ways bridges should not move. His engineering training told him this bridge could not support the weight being demanded of it. His orders told him it had to. In the next 36 hours, Harvey Fraser would have to choose between following the rules he'd learned in engineering school or breaking every one of them to accomplish the impossible. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. What he did next would save thousands of American lives and shorten the war in Europe by months, but it would also require him to gamble with physics, to trust calculations made on scraps of paper in freezing rain, and to send men across a bridge that every instinct told him should be condemned as structurally unsound. The question wasn't whether the bridge would fail. The question was whether it would fail before 400 tanks made it across. The Rhine River in March 1945 represented more than a geographical obstacle. It was a psychological barrier that had protected German territory for centuries. No invading army had forced a crossing of the Rhine since Napoleon in 1805. The river itself was formidable. At Remagen, the Rhine measured approximately 1,200 feet wide. The current ran at 4 to 6 knots. Water temperature hovered just above freezing. The depth varied from 20 to 40 feet. These conditions made assault crossings extraordinarily difficult. Amphibious vehicles struggled against the current. Boats capsized in the cold water. Engineers attempting to construct pontoon bridges faced German artillery fire while working in conditions that caused hypothermia within minutes. Allied planners had assumed any Rhine crossing would require massive preparation. Operation Plunder, the planned British crossing in the north, involved over 1 million men, thousands of artillery pieces, and months of stockpiling supplies. Operation Varsity, the associated airborne assault, would drop over 16,000 paratroopers. The Remagen crossing was supposed to be impossible because nobody planned for it. The Ludendorff Bridge was never supposed to still be standing. German doctrine called for destroying all Rhine bridges before Allied forces could capture them. Engineers had prepared demolition charges on every bridge. The standing orders were clear: destroy the bridges before American tanks could reach them. When American forces approached Remagen on March 7, 1945, the bridge should have been rubble in the river. It wasn't. A series of German mistakes and American speed had left the bridge intact, but severely damaged. German engineers had placed demolition charges incorrectly. The primary charges failed to detonate properly. Emergency backup charges exploded, but only damaged the bridge rather than destroying it. By the time American infantry from the 9th Armored Division reached the bridge at approximately 1 o'clock in the afternoon on March 7th, the structure was standing but clearly compromised. The central span sagged, support cables were severed, the roadway showed crater damage. Structural members exhibited stress fractures. Captain Karl Timmerman led Company A of the 27th Armored Infantry Battalion across the bridge under German fire. His men ran across expecting the bridge to explode beneath them at any moment. German machine gun positions fired from the eastern towers. Artillery shells landed on the bridge deck but Timmerman's infantry made it across and secured a bridgehead on the eastern bank. The capture of the Ludendorff Bridge, intact, was recognized immediately as strategically significant. General Courtney Hodges, commander of First Army, ordered maximum exploitation. General Omar Bradley, commander of 12th Army Group, called it a miracle. General Dwight Eisenhower, Supreme Allied Commander, saw it as the opportunity to break into Germany's industrial heartland weeks ahead of schedule. But capturing the bridge and using the bridge were two entirely different engineering problems. The bridge was damaged. Nobody knew how much weight it could support. Nobody knew how long it would remain standing. German artillery was already targeting it. German aircraft were attempting to bomb it. German frogmen were trying to destroy it with underwater charges. Into this chaos came Lieutenant Colonel Harvey Fraser and the 51st Engineer Combat Battalion. Fraser was 41 years old. In March 1945, he'd graduated from West Point in 1926 with a degree in civil engineering. He had spent the interwar years working on infrastructure projects, including dam construction and highway engineering. He understood load calculations, stress analysis, and structural dynamics. He'd studied bridge engineering at the Army Engineer School at Fort Belvoir, Virginia. He knew how to build bridges. He'd never been asked to save one that was already dying. Fraser arrived at Remagen on the evening of March 7th and conducted his initial assessment. What he found was worse than reported. The bridge's central span had dropped approximately 18 inches. This indicated that primary load-bearing members had failed or were failing. The roadway surface showed multiple craters from both the German demolition attempt and subsequent artillery hits. Each crater represented a point of structural weakness. The western tower showed damage from American artillery fire during the approach to the bridge. The eastern tower had sustained damage from German attempts to destroy their own bridge. Support cables on both sides exhibited severing and fraying. Multiple cables were completely broken. Others were partially separated with individual wire strands, failing under load. The bridge was a railway bridge converted for road use. The original design supported trains weighing far more than tanks, but that design assumed an intact structure. The partial demolition had compromised the structural integrity in ways that were difficult to calculate. Fraser understood immediately that standard engineering analysis would condemn this bridge as unsafe. By every textbook calculation, the structure should not be used for heavy vehicle traffic. But textbook calculations assumed you had alternatives. Fraser had no alternatives. The nearest intact bridge sites were 30 miles north and 40 miles south. Building a pontoon bridge would take days and would be vulnerable to German artillery and air attack. The tactical situation demanded using the Ludendorff Bridge immediately, despite its condition. Fraser made his assessment. The bridge would support vehicular traffic if the loads were carefully controlled. He could not guarantee how long the bridge would last. He could not guarantee it wouldn't collapse during use. He could only say that with proper engineering support and load management, the risk was acceptable given the strategic necessity. His superiors accepted that assessment as they had no choice. The order came down through channels. Move the First Army across the Rhine at Remagen. Priority traffic, armor and mechanized infantry. Time frame: as fast as possible. Specific requirement: 400 Sherman tanks within 36 hours. Fraser looked at those numbers and recognized the impossibility. 400 Sherman tanks at 33 tons each meant 13,200 tons of rolling weight. A standard M4A3 Sherman measured 19 feet 4 inches long, 8 feet 7 inches wide, and 9 feet tall. 400 of them formed a column over 1.5 miles long. When properly spaced, the bridge deck was only 18 feet wide. The tanks would barely fit. Moving 400 tanks across meant continuous traffic for 36 hours. Any delay, any breakdown, any bridge failure would create a catastrophic bottleneck, with tanks backed up for miles, vulnerable to German artillery and air attack. Fraser's engineering team consisted of officers and enlisted men from the 51st Engineer Combat Battalion, augmented by personnel from other engineer units as they became available. Major Richard Sweet served as Fraser's operations officer. Captain John Conlin commanded the bridge repair crews. Lieutenant Edward Mott handled traffic control. Captain William Hogue provided demolitions expertise, essential for clearing German charges that were still attached to the bridge. The first priority was assessment and immediate repair. Fraser's engineers conducted detailed structural surveys while, under German artillery fire, they measured the sag in the central span using surveying equipment. They calculated stress levels in the remaining support cables. They examined every rivet, every weld, every connection point they could access. They discovered that the bridge's load capacity had been reduced by approximately 40% due to the demolition damage. A fully loaded Sherman tank at 33 tons would normally cross with safety margin to spare on an intact railway bridge. On the damaged Ludendorff Bridge, that margin was gone. Fraser calculated that the bridge could support individual tank crossings if the loads were distributed properly. Spacing between vehicles had to be increased. Speed had to be controlled to minimize dynamic loading from vibration and impact. Multiple tanks could not be on the weakest sections simultaneously. The challenge was implementing these controls under combat conditions with hundreds of vehicles waiting to cross and German forces actively trying to destroy the bridge. Fraser developed a traffic control system that was unprecedented in complexity. Engineers established checkpoints on the western approach road 3 miles back from the bridge. Every vehicle approaching the bridge stopped at these checkpoints and received specific crossing instructions. Tank commanders were briefed on speed limits, spacing requirements, and emergency procedures. Each vehicle was assigned a crossing time based on calculated load distribution across the bridge deck. Traffic controllers positioned at both ends of the bridge used radio communications to coordinate the flow. When one tank reached the midpoint of the bridge, the next tank could begin crossing. This spacing ensured that no more than 2 tanks were on the weakest central span at any time. Speed limits were enforced at 5 miles per hour. This minimized dynamic loading from impacts and vibrations. Tank crews hated the slow speed because it meant crossing under German artillery fire for longer periods, but Fraser was absolute. Speed violations meant structural failure, and structural failure meant hundreds of men dying when the bridge collapsed. The traffic control system required enforcement. Military police established control points. Engineers monitored the bridge structure continuously and had authority to halt all traffic if stress levels exceeded safe limits. Radio operators maintained constant communication between all control points. The entire system depended on discipline and coordination under conditions that favored chaos. German forces recognized the bridge's importance and attacked it continuously. Artillery fire landed on and around the bridge 24 hours a day. German gunners had pre-registered targets. They knew the exact ranges. They fired from positions on the eastern hills overlooking the river. High explosive shells detonated on the bridge deck, on the towers, on the approaches. Each impact created additional damage. Each crater made the structure weaker. Fraser's repair crews worked continuously under this fire. They filled craters with timber and steel plating. They welded broken structural members. They replaced severed cables where possible and reinforced them where replacement was impossible. The work was done in freezing rain with German shells landing randomly around them. Casualties among the engineer crews were constant. Men were wounded by shell fragments. Some were killed. The work continued because stopping meant the bridge would fail, and bridge failure meant the end of the Rhine crossing. German aircraft attacked the bridge on March 8th and 9th. Luftwaffe bombers made multiple runs despite Allied air superiority. They dropped bombs that missed the bridge, but created waterspouts in the river that damaged the foundations. They damaged the western approach roads. The attacks forced Fraser to halt traffic temporarily while debris was cleared, but the bridge itself survived the air attacks. German frogmen attempted underwater demolition on the night of March 8th. They swam downstream with explosive charges, intending to attach them to the bridge piers. American engineers had anticipated this and installed underwater defenses, including barbed wire barriers and floating timber booms. Searchlights illuminated the water. Machine gunners fired at any movement in the river. The frogmen were detected and driven off, but the threat remained constant. Fraser had to assume another attempt would come and positioned guards to prevent it. The engineering challenge was complicated by the bridge's original design. The Ludendorff Bridge was built between 1916 and 1918 as a railway bridge during World War I. The design was purely functional. 2 stone towers on each bank, supporting a steel arch truss structure. Total length approximately 1,030 feet. 3 spans, 2 approach spans of approximately 270 feet each. 1 central arch span of approximately 512 feet. The railway deck was designed to support locomotives, weighing far more than Sherman tanks. But that was when the structure was intact. The German demolition charges had been placed on the central arch span. The explosions severed several of the steel arch members and damaged the deck structure. The sag in the central span indicated that the arch was no longer carrying its designed load. The weight was being redistributed to other structural members that were not designed to carry it. This created a structural situation that Fraser found difficult to analyze. The bridge was holding together through redundancy and over-engineering from its original construction. But every hour of use created additional fatigue in the overstressed members. Fraser couldn't calculate exactly when failure would occur. He could only monitor the structure continuously and watch for warning signs. He positioned engineers on the bridge with orders to measure the sag every hour. If the sag increased more than 1 inch, all traffic would halt. If any cable showed signs of imminent failure, all traffic would halt. If any structural member showed new cracking, all traffic would halt. The measurement data came in hourly. The sag increased slowly but measurably. The bridge was continuing to fail. The question was whether it would last 36 hours. On the morning of March the 9th, the tank traffic began in earnest. The first Shermans approached the bridge at dawn. The tank commanders had been briefed. 5 miles per hour, maintain spacing, do not stop on the bridge. If disabled, push the tank off the bridge into the river rather than block traffic. The crews understood the stakes. The first M4A3 Sherman from the 14th Tank Battalion rolled onto the bridge deck at 0600 hours. The tank weighed 33 tons, fully loaded with crew, ammunition, and fuel. The driver maintained 5 miles per hour exactly. The tank crossed the 1,800-foot span in approximately 6 minutes. German artillery fired. Shells landed in the river. 1 shell hit the western tower, but did not stop the crossing. The tank reached the eastern bank and moved inland to make room for the next vehicle. The second tank began crossing as the first reached midpoint. The spacing was perfect. Fraser watched from the western approach. The bridge groaned under the load, but held. The sag in the central span increased, slightly within acceptable limits. The third tank crossed. The fourth. By noon on March 9th, 60 Sherman tanks had crossed. The bridge was still standing. The sag had increased by another ½ inch, but was not yet critical. Fraser authorized continued operations. The crossings continued through the afternoon. Tank after tank, each weighing 33 tons, each depending on calculations made on scraps of paper in freezing rain. By 1800 hours on March 9th, 120 tanks had crossed. The bridge deck showed new stress cracks around the repaired crater areas. Fraser's repair crews welded reinforcing plates over the cracks while traffic continued. The work was done between tank crossings, with engineers scrambling on and off the deck as vehicles approached. It was dangerous, improvised work that violated every safety protocol Fraser had learned at West Point, but it kept the bridge functional. German artillery intensified during the night. They were firing at the traffic backed up on the western approach road. High explosive shells landed among the tanks waiting to cross. Several tanks were hit, crews were killed. The burning vehicles had to be pushed off the road to clear the route. The delays created pressure to speed up the crossing times, but Fraser refused. The speed limit remained 5 miles per hour. The spacing remained constant. Rushing would destroy the bridge and kill everyone on it. By dawn on March 10th, 240 tanks had crossed. The bridge had been in continuous use for 24 hours. The structural monitoring data showed increasing strain. The sag in the central span had increased by 1½ inches total. Several support cables showed new wire strand failures. The bridge was deteriorating, but it was holding. Fraser calculated that they had perhaps 12 more hours before structural failure became inevitable. 12 hours to move 160 more tanks. The math was possible if nothing went wrong. At 0830 hours on March 10th, something went wrong. A Sherman tank from the 3rd Armored Division suffered an engine failure halfway across the bridge. The tank stopped dead on the central span, directly over the weakest section of the bridge. The crew tried to restart the engine. It wouldn't turn over. German artillery fire intensified. Shells landed on both sides of the disabled tank. Fraser's traffic control system had anticipated this. The standing order was clear: if a tank cannot move under its own power, push it off the bridge into the river. But pushing a 33-ton tank off a damaged bridge created its own risks. The pushing force might collapse the deck. Fraser made the decision in seconds. Get it off. Now. A recovery vehicle moved onto the bridge and positioned behind the disabled Sherman. The crew attached towing cables. The recovery vehicle pulled. The disabled tank began moving. Slowly. The steel deck groaned. The bridge swayed visibly. Engineers watching the structural measurements saw the sag increase by half an inch in 30 seconds. If it increased another half inch, Fraser would have to halt all traffic, and the mission would fail. The recovery vehicle pulled harder. The disabled tank rolled forward, meter by meter. The bridge shook. The artillery fire continued. At 08:45 hours, the disabled tank reached the eastern bank and was pulled off the bridge deck. The crisis passed. The sag stabilized. Traffic resumed. By 1400 hours, on March 10th, 300 tanks had crossed. Fraser's calculations showed they were on schedule to complete the mission, but the bridge structure was approaching its limits. The sag now measured 2¼ inches beyond the original damaged state. Multiple cables showed severe strand separation. The deck cracking had extended into previously undamaged sections. The bridge was dying. Every engineer working the site knew it. The question was whether it would last 4 more hours. At 1600 hours, German artillery scored a direct hit on the eastern tower. The shell penetrated the stone structure and exploded inside. The tower sustained heavy damage, but its load-bearing capacity was not immediately compromised. However, the explosion severed additional support cables. Fraser's monitoring team reported that 3 major cables on the southern side of the bridge were now completely failed. The load was being carried entirely by the northern cables and the arch structure. Fraser halted traffic. He needed 10 minutes to assess whether the bridge could continue to function. His engineers examined the cable damage. They calculated the remaining load capacity. The numbers were marginal. The bridge could still support individual tank crossings if the spacing was increased and the speed reduced even further. Fraser made the call: resume traffic, 3 miles per hour, double the spacing between vehicles. These changes would slow the crossing rate considerably, but the alternative was immediate closure and mission failure. The tank crews were informed. 3 miles per hour. The crossings resumed at 1700 hours. Each tank now took approximately 9 minutes to cross. The pace was agonizingly slow. German artillery continued firing. Every minute on the bridge meant more exposure to incoming fire. But the structural requirements were absolute. At 1930 hours on March 10th, tank number 375 crossed. 25 more to go. Fraser checked the structural data. The sag was now 3 inches beyond the original damaged state. This was beyond anything he had considered acceptable during his initial assessment. The bridge should have been closed an hour ago, according to his own safety calculations. But 25 tanks remained. Closing now meant failure. Fraser authorized continued operations. Tank 376 crossed at 1945 hours, 377 at 2000 hours, 378 at 2015 hours. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Each crossing brought new stress. Each crossing moved the bridge closer to catastrophic failure. Fraser stood at the western approach and watched. His engineers reported increasing cable failures. The deck was sagging visibly now. You could see it with the naked eye. The central span was noticeably lower than it had been 30 hours earlier. At 2100 hours on March 10th, tank number 390 crossed. 10 more. Fraser received a report from his monitoring team. The sag had reached 4 inches beyond the original damaged state, and several engineers recommended immediate closure. The risk of catastrophic failure was becoming unacceptable. Fraser considered the recommendation. 10 tanks, approximately 90 minutes at current crossing rates. 90 minutes during which the bridge could collapse at any moment, killing everyone on it and in the immediate vicinity. Against that, 10 Sherman tanks that would not make it across if he closed the bridge now. Each tank represented 5 crew members, 50 men total. Each tank represented tactical capability that First Army needed on the eastern bank. Fraser's decision came down to a calculation that no engineering textbook covered. Which risk was greater? The risk of structural failure killing dozens of men on and near the bridge, or the risk of leaving 10 tanks on the western bank where they were vulnerable to German artillery and useless for the advance into Germany. Fraser gave the order. Continue operations. Monitor the structure every 5 minutes. Prepare to evacuate the bridge on 30 seconds. Notice if failure appears imminent. Tank 391 crossed at 21:15 hours. 392 at 21:30 hours. The bridge was shaking with each crossing now. The entire structure vibrated as the tank treads contacted the steel deck. The vibration was visible from the banks. Soldiers watching from the western approach said it looked like the bridge was alive, moving like a living thing in its death throes. Tank 393 crossed at 21:45 hours. German artillery fire had slackened. Either the German gunners were exhausted or they were running low on ammunition. Fraser's engineers reported no new cable failures in the last 30 minutes. The existing damage was holding stable. Perhaps the bridge would last. At 2200 hours on March 10th, tank number 394 began its crossing. The driver maintained 3 miles per hour exactly. The tank commander stood in the turret watching the deck ahead for obstacles. At the midpoint of the central span, a cable snapped. The sound was like a rifle shot. The bridge deck dropped 3 inches instantly. The Sherman tank lurched sideways. The driver fought for control. The tank slewed left, treads screaming on the steel deck. For a moment, it appeared the tank would slide off the bridge into the Rhine. The driver corrected. The tank straightened. The crossing continued. The tank reached the eastern bank at 22:09 hours. Fraser's engineers examined the cable failure. A major northern support cable had parted under load. The break point showed classic fatigue failure. The individual wire strands had been failing progressively over the past 30 hours. The final strands had given way under the weight of tank 394. The bridge was now supported almost entirely by the arch structure. The cables that remained were providing minimal support. Fraser knew this was the end. 6 more tanks. Perhaps 60 minutes. After that, the bridge would fail regardless of whether traffic continued. The structure had reached the limits of its material strength. He gave permission for the final 6 tanks to cross. Tank 395 crossed at 22:30 hours without incident. 396 at 22:45 hours. At 2300 hours on March 10, 1945, tank number 397, an M4A3 Sherman from the 7th Armored Division, rolled onto the Ludendorff Bridge. The driver knew this was one of the last crossings. He maintained 3 miles per hour. The tank moved steadily across the damaged deck. German artillery, which had been quiet for an hour, opened fire again. Shells landed in the river on both sides of the bridge. One shell hit the western approach road behind the waiting tanks. The explosions lit up the night. The Sherman continued across. At the central span, the deck sagged beneath the weight. The movement was visible. Soldiers on the banks could see the bridge bending. The tank reached the eastern bank at 23:09 hours. 3 more. Tank 398 crossed at 23:20 hours. 2 more. At 23:30 hours, tank 399 began crossing. This was the penultimate vehicle. 1 more after this, and the mission would be complete. 400 Sherman tanks across the Rhine in 36 hours. The impossible accomplished. The tank moved slowly across the shaking bridge. The deck groaned. Steel scraped against steel. At the midpoint, another cable snapped. The bridge swayed. The tank continued. It reached the eastern bank at 23:39 hours. 1 more. Tank number 400. The final Sherman approached the bridge at 23:45 hours. The crew knew they were the last. Every man on both banks watched. Fraser stood at the western approach with his engineering team. They had monitored this bridge for 36 hours. They had repaired it under fire. They had calculated loads and stresses and safety margins. They had gambled with physics and won. 1 more tank and it was over. The Sherman rolled onto the bridge deck. The driver maintained 3 miles per hour. The tank commander stood in the turret and looked ahead at the eastern bank. The bridge shook. The vibration was worse than it had been for any previous crossing. Something was different. The structural resonance had changed. The bridge was at the absolute limit. Fraser's monitoring team reported the sag had increased another half-inch in the last 5 minutes. The bridge was failing actively now. Continuous progressive collapse was beginning. At midnight on March 11, 1945, tank number 400 reached the eastern bank of the Rhine River. The mission was complete. 400 Sherman tanks had crossed the Ludendorff Bridge in 36 hours. Fraser immediately ordered all traffic halted. No more vehicles would cross until the bridge could be fully assessed and repaired. The assessment came back within an hour. The bridge was beyond economical repair. The structural damage was too extensive. The fatigue in the remaining load-bearing members was too advanced. The bridge would fail within days, regardless of whether it was used further. Pontoon bridges were already under construction upstream and downstream of Remagen. Those bridges would carry traffic once completed. The Ludendorff Bridge had served its purpose. At 1500 hours on March 17, 1945, the Ludendorff Bridge collapsed. The central span failed catastrophically. The arch structure, which had been carrying almost the entire load since the cables failed, finally gave way. The steel members buckled under fatigue stress. The deck dropped into the Rhine River. 28 American engineers were working on the bridge at the time, conducting repairs and trying to extend its service life. All 28 went into the river. When the bridge collapsed, 18 were rescued. The 10 drowned or died from injuries. The collapse happened at 1500 hours in the afternoon, in daylight, with good visibility. If it had happened during the night, crossings when hundreds of tanks were using the bridge, the casualties would have been in the hundreds or thousands. Fraser's calculations had been correct. The bridge lasted exactly as long as he predicted it would. The structural failure occurred days after the 400 tanks crossed, not during the crossing operations. The timing validated everything Fraser had done. The risk had been acceptable. The engineering had been sound. The mission had succeeded. The strategic impact of the Remagen bridgehead was immediate and enormous. First Army poured reinforcements across the Rhine through the captured bridge and the rapidly constructed pontoon bridges nearby. By March 15th, 4 days after the last Sherman crossed, over 25,000 vehicles had moved to the eastern bank. 8 divisions crossed at Remagen in the first week. German forces attempting to contain the bridgehead were overwhelmed. The bridgehead expanded to 25 miles wide and 10 miles deep within 10 days. This penetration deep into Germany threatened to encircle entire German army groups. German forces that had been positioned to defend the Rhine found themselves outflanked. Units that should have been establishing defensive positions in Germany's interior were instead fighting to contain the Remagen bridgehead. The effect on German morale was devastating. The Rhine was supposed to be impregnable. It was the last major barrier. If the Americans could cross the Rhine against opposition, there was nowhere left to make a stand. German commanders knew the war was lost. Many units began surrendering rather than fighting to the death. The Remagen crossing influenced Allied strategy for the remainder of the war. The success at Remagen convinced Eisenhower to shift forces south to exploit the breakthrough. Patton's Third Army crossed the Rhine at Oppenheim on March 22nd. Montgomery's 21st Army Group crossed in the north on March 23rd as part of Operation Plunder. Within 2 weeks, Allied forces had multiple bridgeheads across the Rhine. The river barrier that was supposed to delay the Allied advance for months was breached in days. The war in Europe ended on May 8, 1945, less than 8 weeks after the Remagen crossing. Historical analysis suggests the Remagen bridgehead shortened the war by weeks and possibly months. German forces that might have prolonged resistance were instead forced into rapid retreat and surrender. The capture and use of the Ludendorff Bridge at Remagen is studied in military engineering courses as a case study in risk assessment under combat conditions. Fraser's decision-making process is analyzed in detail. He faced a situation where standard engineering practices would have required closing the bridge. Textbook safety margins were exceeded, structural damage was extensive and progressive. Any civilian bridge in similar condition would have been condemned immediately and closed to all traffic. But Fraser recognized that military necessity sometimes requires accepting risks that would be unacceptable in peacetime. He calculated those risks as carefully as possible. He monitored the structure continuously. He implemented controls to minimize the danger. He never gambled blindly. Every decision was based on engineering analysis, even when that analysis showed he was operating beyond normal safety limits. The 400 Sherman tanks that crossed at Remagen represented only a small fraction of the total Allied armor in Europe. First Army had thousands of tanks available. Losing 400 would have been painful, but not strategically decisive. But those 400 tanks crossed days or weeks before they could have crossed anywhere else. They provided armored support for the infantry establishing the bridgehead. They spearheaded the breakout from the bridgehead into Germany's interior. They were the exploitation force that turned a tactical bridge capture into a strategic penetration. Fraser's engineering made that possible. His willingness to push the damaged bridge to its absolute limits allowed those tanks to cross when crossing mattered most. The 10 engineers who died when the Ludendorff Bridge collapsed on March 17th were casualties of the same combat engineering mission that saved the bridge long enough to accomplish its purpose. They died trying to extend the bridge's service life beyond what Fraser had calculated it could sustain. Their deaths were a reminder that military engineering in combat zones is inherently dangerous work. Fraser was promoted to colonel after the war and continued serving in the Army Corps of Engineers. He worked on reconstruction projects in Europe and later on infrastructure development in the United States. He rarely spoke about Remagen publicly. When asked, he credited his enlisted engineers who did the actual repair work under fire. He never claimed personal credit for the decisions that made the crossing possible. He understood that leadership in engineering comes down to making calculations that balance technical requirements against tactical necessity and then accepting responsibility for those calculations. Harvey Fraser died in 1972 at age 68. He was buried at Arlington National Cemetery with full military honors. His obituary mentioned his service at Remagen, but most accounts focused on his peacetime engineering work. The bridge crossing that defined his career received only brief mention. The Ludendorff Bridge was never rebuilt after its collapse. The towers remain on both banks of the Rhine as memorials. The Western Tower houses a small museum dedicated to the Battle of Remagen and the bridge crossing. The museum displays photographs of the damaged bridge, artifacts recovered from the river, and documents detailing the engineering work that kept the structure functional long enough to accomplish the mission. The Sherman tanks that crossed at Remagen continued fighting for another 8 weeks. They participated in the advance across Germany. They fought in the Ruhr pocket encirclement. They were present at the Elbe River when American and Soviet forces met. Some of those tanks survived the war and were shipped back to the United States for demobilization. Others were lost in combat. A few are preserved in museums. The men who designed the Ludendorff Bridge in 1916 never anticipated it would be used the way Fraser used it in 1945. They designed a railway bridge to carry trains across the Rhine during World War I. They engineered it with safety margins appropriate for peacetime operations. They never imagined it would be damaged by demolition charges, held together by improvised repairs, and pushed beyond every safety limit to move 400 tanks in 36 hours. That's the paradox of military engineering. Structures designed for one purpose get used for entirely different purposes under conditions their designers never considered. Success requires engineers who understand the original design well enough to know when and how it can be safely exceeded. Fraser understood that. He knew the bridge's design. He understood its failure modes. He calculated how far he could push it before catastrophic collapse became inevitable. Then he pushed it exactly that far and not 1 inch further. That's engineering judgment at its finest. Not following the textbook, but understanding the principles behind the textbook well enough to know when they can be bent and when they cannot. The story of the Ludendorff Bridge crossing deserves to be remembered because it demonstrates what military engineering makes possible. Infantry can capture bridges, artillery can support bridgeheads, air power can provide cover, but none of that matters if engineers cannot keep the bridge standing long enough for armor to cross. Fraser and his engineers kept a dying bridge alive for 36 critical hours. They worked under fire. They made calculations with incomplete information. They accepted risks that peacetime engineers would reject. They succeeded because they understood both the engineering and the stakes. 400 Sherman tanks crossed the Rhine at Remagen in 36 hours because one engineer understood that sometimes following the rules means accepting failure, and sometimes achieving victory requires breaking every rule except the fundamental laws of physics. Fraser broke the rules. He pushed the bridge beyond its rated capacity. He kept traffic moving when safety protocols said stop. He gambled with structural failure and won. The bridge collapsed a week later, exactly as he predicted it would. But by then, 400 tanks were on the eastern bank, and the war was won. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.